Hi, I'm Patrick Reagan, and welcome to the Network Switches Part 4 Switch Architecture. In this video, we'll shift into looking how to architect a switch infrastructure so that you can get the most of your network infrastructure. Topics include 3-tier, collapsed core, and spine and leaf architectures, and looks at north-south and east-west traffic. As always, stick around for the practice questions at the end to test your knowledge and help you prepare for the Network Plus exam. If you find this video helpful, don't forget to click the like button. And if you have not already, subscribe to the Pat Has Your Back channel for more tech training content and networking know-how. Network switch architecture refers to the structure, design, or layout of how switches are arranged, connected, and configured within a network to optimize performance, scalability, reliability, and manageability that provides consistent and a secure foundation. It provides the following: scalability that allows for the network to grow as you add more users, devices, and applications. Performance optimization, which allows for low latency, high throughput connections for critical apps. Security supports security by allowing VLANs, access control lists, port security, and segmentation to be applied to the network. Redundancy and resilience, using redundant uplinks and spanning tree protocol, or STP, to ensure failover capabilities and network uptime. Troubleshooting and management. Clear layers and functions allow for easier troubleshooting and monitoring and configuration consistencies. Traffic segmentation and control. Use of VLANs, QoS, and traffic shaping keeps each traffic type optimized and isolated as needed. And provides foundation for automation in SDN. By having a modular, standardized architecture, enables programmability and dynamic reconfiguration of network resources. Network traffic can describe the direction of data flow within a network, particularly within the data center. It can be broken down to east-west, which is the lateral movement within the same segment or data center, which includes server to server, and north-south, which is vertical movement between internal and external networks, such as into and out of the data center, such as client to server. East-west traffic refers to the data traffic that moves laterally within the same segment or data center, typically between servers or between virtual machines within the same data center. It is used in server-to-server communications, whereas applications where services need to communicate with each other, such as in distributed computing environments, microservice architecture, and virtualized environments. Where large volume of data exchange, especially environments with heavy inter-service communications, and where applications usually require low latency and high bandwidth to ensure efficient communication between servers and VMs. East-west traffic is used for data replication between storage devices, communications between application servers and database servers, service-to-service communications in a microservices architecture, and virtual machine migration within the same data center. North-south traffic refers to data traffic that moves between internal and external networks, such as into and out of the data center, typically between the data center and external networks, such as the internet or other data centers. Think of north-south as ingress-egress to an outside device. It is used in client-server communication, which involves traffic between end users and servers within the data center. It often passes through firewalls, load balancers, and other security devices to control access and protect the data center. The volume can vary significantly depending on the number of external requests and interactions. Examples of north-south traffic may include a user accessing a web application hosted in the local data center, data backup to a remote location, traffic between a corporate data center and cloud services, an incoming user request to a web server, or outgoing responses from an application server. The 3-tier hierarchy model is a common network architecture used in large enterprise to design scalability and manageable enterprise networks. This model divides the network into 3 distinct layers, each with its own specific functions and characteristics. The layers include core layer, distribution layer, and access layer. The core layer is responsible for high-speed and reliable data transport across the network. It acts as the backbone of the network, connecting different distribution layer devices. High-performance layer 3 switches, or core routers are best suited for the core layer due to their ability to handle high speed, large volume traffic with minimum latency, ensure reliability and redundancy, and provide advanced routing capabilities. Characteristics include high-speed forwarding with minimum latency, high availability and redundancy, simple and stable, avoiding any complex packet manipulation, and it is designed for fast and efficient data transfer, usually with high-capacity switches and routers. The distribution layer serves as an interface between the core and access layers, providing policy-based connectivity. It aggregates data received from the access layer and forwards it to the core layer. Layer 3 switches or multi-layer switches are best suited for the distribution layer due to the routing capabilities, support for network policies, high performance, redundancy features, and advanced functionalities. Characteristics include policy implementation, routing between different VLANs and subnets, load balancing and redundancy, and aggregation of multiple access layer switches. The access layer provides end devices such as computers, printers, and IP phones with network access. It is the layer where user devices connect to the network. It is recommended to use layer 2 switches because they generally have a high number of ports to connect a large number of end devices and are usually more cost-effective than layer 3 or multi-layer switches. Characteristics include connectivity for end devices, implementation of port security measures, VLAN assignments, and support for Power over Ethernet or PoE for connected devices like IP phones and wireless access points. Benefits of the 3-tier hierarchy model include scalability. Each layer can be scaled independently, making it easier to expand the network as needed. Performance. The separation of roles allow for optimized performance with the core layer focusing on speed and the access layer focusing on connectivity. Manageability. Clear demarcations of functions makes the network easier to manage, troubleshoot, and maintain. Redundancy and reliability. The hierarchy design allows for better implementation of redundancy and failover mechanisms, increasing network reliability. Flexibility. Policies and configurations can be applied at the distribution layer without affecting the core or access layers, providing flexibility in network management. By adhering to the 3-tier hierarchy model, the network is structured in a way that supports scalability, performance, and ease of management, making it suitable for enterprise environments. The disadvantage of 3-tier hierarchy models include the architecture is complex, and while it does offer fewer single points of failure, its cost is high. Now imagine a corporate network with several departments, each requiring reliable and high-speed connectivity. At the core layer, you would use high-capacity switches in the data center connected to all distribution switches across the campus, ensuring fast and resilient backbone connectivity. For the distribution layer, switches in each building aggregate traffic from the access layer and enforce policies like traffic shaping, routing between different departmental VLANs, and implementing access controls. For the access layer, switches in each floor or office provide network ports for computers, IP phones, and wireless access points, ensuring devices can connect to the network securely and efficiently. 2-tier architecture, also known as collapsed core architecture in networking, simplifies network design by reducing the number of layers to just 2. The access layer and the distribution/core layer, which is combined into a single layer. This architecture is typically used in smaller networks where the 3-tier model may be overly complex or unnecessary. It maintains essential features like redundancy, policy implementation, and high-speed connectivity while reducing complexity and cost. The distribution core layer combines the roles of distribution and core layers from the 3-tier model. It aggregates traffic from the access layer and provides high-speed data transport across the network. Its characteristics include high-speed switching and routing, implements policies like access control list and quality of service, provides redundancy and load balancing, and connects different access layer switches, and may connect to external networks like the internet. An ideal 2-tier architecture is to use 2 distribution or core switches to reduce a single point of failure. The devices best suited for the core layer and the collapsed core architecture are typically layer 3 switches or multi-layer switches with high performance and advanced routing capabilities. The access layer provides connectivity to end devices such as computers, printers, IP phones, and wireless access points. In a collapsed core architecture system, Layer 2 switches are best suited for the access layer due to the port density, cost effectiveness, VLAN support, and basic switching capabilities. Characteristics include directly connects end users to the network, implements security features like port security and VLAN assignments, and supports Power over Ethernet or PoE for connected devices. The benefits of two-tier collapsed core architecture include simplifies network design and management by reducing the number of layers, easier to configure, monitor, and troubleshoot, fewer devices and infrastructures are needed, reducing capital and operational expenditures, and suitable for smaller environments where a full three-tier architecture may be unnecessary. While not as scalable as a three-tier architecture, two-tier architecture can still support growth to a certain extent by adding more access layer switches and ensuring the distribution core layers has sufficient capacity. It's easier to implement changes and updates since there are fewer layers to manage. In a two-tier collapsed core architecture, for a smaller remote site, you typically assign a single collapsed distribution core device and one or more access layer switches, not just the access layer alone. While access switches handle local devices connectivity, you still need one core distribution device per site to handle routing and upstream connectivity. You would only consider a single access switch with no core if you have a very basic needs and you have a layer 2 VLAN backhaul to HQ, whereas VLAN does not perform local routing and instead sends all VLAN traffic over a layer 2 tunnel back to the headquarters where the routing and services like DHCP and firewalling happen. Imagine a small to medium-sized business with a single office building. For the access layer, switches on each floor of the building connect end devices like desktop computers, IP phones, and wireless access points. For the distribution and core layer, a few high-capacity switches in the server room aggregate traffic from the access layer switches, implement network policies, and connect to the internet router. Spine and leaf architecture is a network topology commonly used in data centers and large-scale cloud environments to provide high-speed, low-latency, and scalable network connectivity. It is designed to overcome the limitations of traditional three-tier architectures by ensuring consistent and predictable performance. Spine switches act as the core layer, providing high-speed interconnectivity between all leaf switches. The spine switches are layer 3 switches, which serves as the network's backbone and helps in routing and forwarding. It's recommended to use high-performance layer 3 switches because of high throughput, low latency, high port density, and advanced routing capabilities. Spine switches only connect to leaf switches and not to each other, simplifying the network design and enhancing performance. Note, you don't need direct connectivity between the spine switches because every leaf switch connects to all spine switches, which provides redundancy. Leaf switches serves as the access layer, connecting directly to servers, storage devices, and other networked equipment. All leaf switches connect to all spine switches, ensure there are multiple paths for data to travel, which improves redundancy and load balancing. The leaf switches are basically layer 2 switches, which help connect storage devices and servers. Spine and leaf architecture uses equal cost multipath routing, or ECMP, which allows traffic to be distributed evenly across multiple paths, optimizing bandwidth usage and minimizing congestion. It enhances fault tolerance and load balancing by using multiple parallel paths. It supports horizontal scaling by easily adding more leaf switches and spine switches without significant redesign. It supports rapid growth in high-density environments typical of modern data centers. It ensures consistent and predictable low-latency connections by limiting the number of hops between devices. It is optimized for east-west traffic or server-to-server communications, which is common in data centers. The uniform and predictable layout simplifies management, monitoring, and troubleshooting, while reduces operational complexity and enhances network reliability. When planning the switch architecture, you should consider the following. Use three-tier if you're a larger organization with layered control needs and growth plans. Used at the main site or headquarters and large campus locations. You don't usually extend a single three-tier architecture across sites. Each large site replicates the three-tier model locally. Use two-tier if you're a smaller org looking for simplicity and moderate performance. It provides lower cost and complexity, which makes this ideal for small and medium branch sites. It offers centralized policies, including firewalls and routing, that can be controlled from the HQ. It easily fits into the hub and spoke WAN topology. Use spine and leaf if you're running a data center or need scalable, low latency, high throughput switching. Use a flat layer 2 access network with managed switches, preferably with VLAN support, or possibly a two-tier collapse core if you have a remote site with a small number of devices. If you expect rapid growth, plan for a scalable switch, such as scalable or modular switches. If high uptime is critical, consider adding redundant uplinks or PoE switches for APs and phones. Here's a table summarizing the various architectures. As you can see, you should use three-tier for large enterprises and two-tier collapse for small medium networks. For data centers, you should use the spine and leaf, which offers low latency, which is needed for heavy east-west traffic. If you have one large corporate network, 5 medium networks, and 10 small networks connected with WAN links, you may consider a hybrid of both architectures. The corporate HQ would be a three-tier hierarchy, that is high scale, central routing, and segmentation that offers central aggregation point for WANs and services, including DHCP, DNS, and firewalls. The medium sites could use two-tier collapse core, which has balanced cost, performance, and scalability while allowing VLANs and local routing. Small sites will have flat or light two-tier, which is simplicity, low cost, and minimum local services with minimum VLANs and possibly centralized routing via WAN or SD-WAN. Question: which of the following architectures reduce network latency by enforcing a limit on the number of switching devices on the frame's path between any internal hosts? Answer: spine and leaf. Question: which of the following is the benefit of the spine and leaf network topology? Answer: stable network latency. Question: which of the following describes traffic going in and out of the data center from the internet? Answer: north-south. Question: which of the following factors should you consider when evaluating a firewall to protect east-west traffic? Answer: traffic between VMs running on different hosts. Question: which of the following is most likely to generate significant east-west traffic in a data center? Answer: a duplication of hosted virtual server to another physical server for redundancy. Question: Which of the following would be best suited for use at the access layer in a three-tier architecture system? Answer: Layer 2 switch. For more information, refer to these sites. In summary, the three-tier hierarchy model is a common network architecture used in large enterprise to design scalable and manageable enterprise networks. The three-tier model divides the network into three distinct layers, each with its own specific functions and characteristics, including core layer, distribution layer, and access layer. Two-tier architecture, also known as collapsed core architecture in networking, simplifies the network design by reducing the number of layers to just two: access layer and distribution/core layer, which is combined into a single layer. Spine and leaf architecture is a network topology commonly used in data centers in large-scale cloud environments to provide high-speed, low-latency, and scalable network connectivity. Network traffic can describe the direction of data flow within a network, particularly within a data center. Network traffic can be broken down to east-west, which is lateral movement within the data center or server to server, or north-south, which is vertical movement into and out of the data center or client to server. Thank you for watching this video. The next video will be Switches, Part 5, Introduction to Cisco Switches. If you like this video, click the like button, and if you have not already, subscribe to the Pat Has Your Back channel. Thank you.